Tonight, we're going to talk about why finding another civilization or ever being found by one may be physically impossible. Not the kind of impossible that gets solved with better technology or more time. The kind that's built into the laws this universe runs on. Because most people think the silence out there is a waiting game, that we just haven't aimed at the right star yet. That patience and better instruments will eventually change the answer. But the physics says something different. The obstacles between us and anyone else out there aren't problems waiting to be solved. They're built into the fabric of space-time itself, stacked on top of another, each one making contact less possible than the last. By the end of tonight, you're going to understand why the universe isn't hiding anyone from us, but that it was built in a way that contact between civilizations may never have been possible in the first place. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The universe is about 13.8 billion years old. The Milky Way alone contains somewhere between 200 billion and 400 billion stars. Astronomers estimate that roughly half of those stars have planetary systems. Of those planetary systems, a significant fraction contain at least one planet in what astronomers call the habitable zone, the range of distance from a star where liquid water can exist on a planet's surface. Even if only a tiny fraction of those worlds ever developed life, and an even tinier fraction developed intelligent life, and a still tinier fraction of those ever built radio transmitters or spacecraft, the numbers should still produce millions of civilizations across the history of the galaxy, some of them with a head start on us of hundreds of millions of years. A civilization that far ahead could have crossed the entire galaxy, left signals so loud and so everywhere that silence would be impossible. They should be unmistakable. And yet, silence. No signals, no artifacts, no visitors, no footprints, nothing. This is what became known as the Fermi Paradox, and it remains one of the most profound unsolved problems in all of science. There are dozens of proposed solutions. Maybe intelligent life is rarer than we think. Maybe civilizations tend to destroy themselves before they reach the stars. Maybe they're out there but hiding. Maybe they're communicating in ways we can't detect. Maybe we're just not listening to the right frequencies at the right times. All of those might contribute something to the answer. But tonight, we're going to go deeper than the standard list. Because beneath the Fermi Paradox, there's a more disturbing possibility that most discussions don't fully explore. The universe may not be failing to produce civilizations at the same time we exist. It may be actively structured in a way that ensures any civilizations that do arise are separated by barriers that are, for all practical purposes, permanent. Because of physics. Because of the way time, space, and energy work at the most fundamental level. The universe isn't cruel about it. It's indifferent. And that's somehow worse. Start with light speed. The speed of light in a vacuum is approximately 186,000 miles per second. That's fast in a way that's genuinely hard to absorb. In 1 second, a beam of light could travel around the Earth's equator about 7.5 times. In 8 minutes and 20 seconds, it crosses the 93 million miles between Earth and the Sun, and in approximately 4.24 years, it reaches Proxima Centauri, the nearest star to our solar system. Now, here's the problem. The speed of light isn't just the fastest thing that currently exists. It's the fastest thing that can exist. under the laws of physics as we understand them. Einstein's special theory of relativity, confirmed by every experiment ever designed to test it, establishes that nothing with mass can reach the speed of light, not approach it and keep going, not sneak past it with enough energy. The closer you get to light speed, the more energy you need to go faster, and that energy requirement doesn't rise steeply. It rises asymptotically, toward infinity. At 90% of light speed, your effective mass has more than doubled from the perspective of anyone watching you. At 99%, it's multiplied by more than 7. At 99.9%, it's multiplied by more than 22. At 99.999%, it's almost 224 times your rest mass. To actually reach the speed of light, you would need infinite energy. The universe contains a finite amount of energy, so the speed of light is not just a practical barrier. It's a hard limit baked into the structure of reality. This means that even if we somehow built a spacecraft tomorrow that could travel at 90% of the speed of light, something no engineering we can currently conceive of could achieve it, would still take us 4.7 years to reach the nearest star. And that's the nearest star, not the nearest interesting star, not the nearest planet confirmed to have an oxygen atmosphere, just the nearest point of light you can see on a clear night that isn't our own sun. The galaxy is 100,000 light-years across. At 90% of the speed of light, crossing it would take about 111,000 years. There are 2 trillion galaxies in the observable universe. The nearest major galaxy beyond our own, the Andromeda Galaxy, sits 2.5 million light-years away. Light itself needs 2.5 million years to make that crossing. There is no shortcut. There is no tunnel through. The speed of light is not a ceiling to be broken through with better engineering. It is the shape of the universe. It's the rate at which information propagates through the fabric of space-time. And once you truly accept that, the silence of the cosmos stops being puzzling. It starts looking inevitable. But light speed is just the beginning of the problem. Because even if we accepted that communication at light speed was the only option, that would still mean something remarkable could be possible in principle. You could send a signal, a laser pulse, a focused radio beam, something that travels at light speed and carries information. You couldn't have a conversation in real time across interstellar distances, but you could at least shout into the dark and hope someone hears the echo eventually. We've been doing that since the early 20th century, unintentionally. Radio waves from our first television broadcasts have been expanding outward from Earth at the speed of light since the 1920s and 1930s. They've now traveled roughly 90 to 100 light-years from Earth, spreading, in all directions, an expanding sphere of unintentional noise. That sounds like a significant bubble advertising our existence. Except it isn't. The signal strength of any electromagnetic transmission drops with the square of the distance. Double the distance, the signal is 4 times weaker. Triple it, 9 times weaker. 10 times the distance, 100 times weaker. By the time those signals have traveled even a few light years, they're so attenuated that they fall below the background noise of the cosmos. A civilization 100 light years away, with the most sensitive radio telescopes we can imagine, would not be able to distinguish the signal of a commercial television broadcast from the background hiss of the universe. Our radio bubble is, in practical terms, transparent. We have been shouting into a noise floor that swallows our voice completely. And we have to assume any other civilization faces the same fundamental physics. Their broadcasts are also being swallowed. This creates a quiet so deep, it's almost indistinguishable from absolute solitude. The universe communicates at light speed, and even light speed isn't fast enough to make a bubble. 100 light-years across feel like anything other than a whisper drowning in static. The physics doesn't care about intent. A civilization broadcasting at full power and a civilization that never existed look essentially identical from far enough away. That's a deeply strange property of the cosmos to sit with for a moment. Effort and absence produce the same observable result across interstellar distances. Now, think about time. Not the distances between civilizations in space, but the distances between them in time. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Modern humans have existed for something like 300,000 years. We've had radio technology for about 130 years. We've had spaceflight for roughly 70 years. The entire technological window of human civilization, the period during which we could, in principle, make or receive a radio signal, is about 130 years long. 130 years, against a 13.5 billion-year-old universe. Now, think about what that means on a cosmic timescale. If a civilization formed 10 billion years ago, had a technological window of 10,000 years, and then collapsed, exhausted its resources, or simply moved on to communication methods we don't understand, then their window of transmitting detectable signals would have closed almost 10 billion years ago. We were not here then. We couldn't have heard them, and they couldn't have waited. The universe doesn't synchronize the appearance of civilizations. Stars form, burn, and end their lives on their own schedules, set by their masses and their starting conditions. Planets coalesce, cool, and develop conditions for life across billions of years of independent timelines that are not coordinated with each other in any way. Even if the galaxy produced 10 million technological civilizations over its entire history, the odds that any two of them would overlap in time, both existing and transmitting within the same window, are genuinely small. Think about it this way: 10 million candles being lit and extinguished randomly across a darkened room over the course of 1,000,000 seconds. At any given moment, you might have dozens lit at once. But if each candle only burns for a fraction of a second, you'll often see none at all. And if you're one of those candles yourself, you have no way of knowing where the others burned. You can only report that the room around you appears dark. That's the temporal problem. It compounds the spatial problem. Two civilizations separated by 100 light years might both have existed, both had radio technology, and still have missed each other by 10,000 years. One rose and fell before the other's first signals could have arrived. The other rose and fell before the first one's broadcasts even reached them. In a universe this old, this vast, and this structurally indifferent to synchronization, parallel existence across the cosmic neighborhood is the exception, not the rule. The universe is producing things that come and go. Civilizations are among those things. And coming and going on different schedules, across distances that take light years to cross, might be the fundamental condition of intelligence in this cosmos. Not contact, isolation, not dialogue, monologue. Each civilization speaking into a universe that, by the time its voice reaches the distances required, has already changed the answer. This brings us to a barrier that people rarely think about carefully in this context. The speed of light doesn't just limit travel, it limits knowledge. It limits what you can even know about the universe around you. When you look at the Andromeda galaxy on a clear dark night, a faint smear of light barely visible to the naked eye, The light entering your eyes left that galaxy 2.5 million years ago. You're not seeing Andromeda as it is. You're seeing Andromeda as it was 2.5 million years ago, when our ancestors were walking upright on the African savanna, chipping stone tools, and had no concept of galaxies or light or what any of it meant. The further out you look, the further back in time you see. The most distant objects visible to our telescopes are being observed as they existed roughly 13 billion years ago, when the universe was only a few 100 million years old. That's all we can ever have about those regions. Whatever those galaxies look like today, whatever is happening in them right now, by any definition of now, we will not receive that information for billions of years. This is not a technological limitation. It is the consequence of living inside a universe where the speed of information has a hard ceiling and where that ceiling is far slower than the scale of the universe demands. There is a sphere around every point in the universe called the observable universe. Bounded by the distance light has had time to travel since the Big Bang. Beyond that sphere, no information has yet reached us. Not because those regions don't exist, because the universe isn't old enough for light from those regions to have made the journey yet. The radius of our observable universe is about 46 billion light-years in every direction. The total universe is almost certainly vastly larger than this, possibly infinite. We will never see beyond our observable horizon, not with better telescopes, not with more time, because the universe is expanding. And beyond a certain distance, that expansion is carrying regions away from us faster than light can cross the growing gap. There is a hard edge to what we can ever know, and that edge is built into the geometry of expanding space-time. Any civilization beyond our observable horizon is not just hard to reach. They are causally disconnected from us. No message can travel between us in either direction, not ever. The universe isn't hiding them from us. It has structured space-time so that we are on separate islands that can never exchange even a single photon. This isn't a problem to be solved. It's a property of the cosmos, a property that creates isolated pockets of knowable reality, separated by stretches of space-time that are causally sealed off from each other by the expansion itself. The universe manufactures isolation at the largest scales, and below those scales, it constructs it layer by layer. But stay within the observable universe. Set aside the civilizations beyond our cosmic horizon. Even within the portion of the universe, we can, in principle, observe the barriers compound in layers, each one building on the last. The size of the galaxy itself is a barrier most people underestimate. The Milky Way is approximately 100,000 light-years in diameter. It contains between 200 billion and 400 billion stars. Within it, astronomers have identified what they call the galactic habitable zone, a ring-shaped region of the galaxy where conditions are most favorable for the development of complex life. The distribution of potentially life-bearing worlds is not uniform. The galactic center, for all its concentration of stars, is actually hostile territory. Sagittarius A, the supermassive black hole at the core of the Milky Way, has a mass of about 4 million suns. The region around it is dense with radiation, packed with massive young stars that explode as supernovae at rates far higher than in the quieter outer regions. High-energy gamma-ray bursts, intense X-ray radiation from active processes near the central black hole. The center of the galaxy is not where you want a planet if you're trying to develop billions of years of stable surface conditions for complex life. The outer edges of the galaxy also present problems. Fewer heavy elements, because stars of the kind that produce the carbon, oxygen, iron, and silicon needed to build rocky planets. And complex chemistry became more common over time, as previous stellar generations processed hydrogen and helium into heavier elements and then distributed those elements through supernovae. The most element-rich environments, the ones most favorable to planet formation and complex chemistry, tend to be in an intermediate ring between the radiation-drenched core and the element-poor outskirts. Our own Sun sits at about 26,000 light-years from the galactic center, a reasonable address as galactic real estate goes. But even within the galactic habitable zone, the distances are immense. Two civilizations in the same favorable region could easily be separated by 10,000 light-years. A signal between them takes 10,000 years to arrive. By the time it does, the civilization that sent it may have had a different form of government, a different biology, or no government and no biology at all. The galaxy is big enough to contain millions of civilizations that are effectively isolated from each other simply by distance. Even if every one of them is broadcasting at full power continuously for thousands of years. Full power and full commitment get you nothing when the medium between sender and receiver erases the signal before it arrives with any useful strength. Now consider something about the night sky that we almost never discuss. The stars you see from Earth are not a uniform sample of the galaxy. They're the stars within a few thousand light-years of us, at most. The vast majority of the Milky Way's stars are hidden behind clouds of interstellar gas and dust. The galactic center itself is completely invisible to the naked eye in optical wavelengths. We had to build radio telescopes and infrared observatories before we could even see what was happening in the inner galaxy. Sagittarius A, the supermassive black hole at the center of our galaxy, was confirmed as a black hole only because we could observe it in radio and infrared wavelengths that pierce the obscuring dust. In visible light, it's hidden. The same clouds of gas and dust that obscure our view also scatter and absorb signals traveling through them. A radio signal originating somewhere in the dense star-forming regions of the inner galaxy and trying to reach a planet on the far side would lose enormous amounts of its intensity passing through those clouds. The galaxy is not a transparent medium. It's a complex, structured environment full of material that scatters, absorbs, and distorts electromagnetic signals at different rates depending on frequency, direction, and the specific distribution of material along any given line of sight. This matters for any systematic search for signals from other civilizations in a direct way. Our searches have necessarily been shallow. We've looked at specific regions, at specific frequencies, for limited durations. The number of stars we've meaningfully examined for signals of the types we're looking for is a tiny fraction of the stars in the galaxy. Even the most comprehensive programs to date have covered only a small slice of the available parameter space. Different frequency bands, different signal types, different sky directions, different durations, different polarizations. We haven't listened to the galaxy. We've pressed our ear briefly against a very small section of it. And even that small section doesn't return what's actually out there, because the galaxy itself filters and attenuates what passes through it. This doesn't mean no one is out there. It means the search is incomparably harder than most people assume, and the galaxy itself makes it harder. Not through malice, through its physical structure. Dense clouds between us and anyone who might be transmitting. Distances that smear signals below the noise floor. A geometry that puts potential civilizations in corners of the galaxy we've barely begun to examine. we are conducting something genuinely heroic in scope. And we haven't found anything. Both of those things are true simultaneously, and they're not contradictory. They're the honest description of where we are. There's a concept in the study of cosmic origins that becomes directly relevant here. The universe's capacity to produce the chemistry that underlies life has changed dramatically over its history. The Big Bang produced hydrogen and helium almost exclusively. No carbon, no oxygen, no silicon, no iron. None of the heavier elements that form the basis of rocky planets, organic chemistry, and biological complexity. Every heavier element in the periodic table was forged inside stars or in the violent events that end stellar lives. Through fusion reactions in stellar cores, stars convert lighter elements into heavier ones. Helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, and in the cataclysmic deaths of massive stars, supernova explosions release enough energy to create elements heavier than iron and scatter all of these products across surrounding space. Over billions of years, that enriched material becomes part of new star-forming clouds, and new generations of stars form with higher and higher proportions of heavy elements. Our Sun is a third-generation star, or possibly later. It formed from material that had already passed through at least 2 previous stellar generations. The iron in your blood, the oxygen in your lungs, the calcium in your bones, the carbon in every organic molecule in your body, all of it was processed through at least one stellar furnace and scattered into space before gravity pulled it together again into the cloud that became our solar system 4.5 billion years ago. This is not philosophy. This is documented stellar evolution, confirmed by spectroscopic analysis of stars across different ages and populations. And it has a profound implication for the question of life in the universe. The universe's capacity to produce rocky planets with the chemical richness to support life increased over time. The earliest stars, the so-called population 3 stars that formed in the first few 100 million years after the Big Bang, were made of almost pure hydrogen and helium. They had no planets the way we understand planets. No chemistry complex enough for biology. Life, at least the kind built on organic carbon chemistry, required a universe old enough to have run several stellar generations before conditions were suitable anywhere. The universe was roughly 8 to 10 billion years old before the kinds of planetary systems that could harbor complex life became common throughout the galaxy. And even then, the development of life, then complex life, then intelligent life, took hundreds of millions or billions of years on any given world. The window during which the universe has been capable of producing civilizations, even vaguely like ours, is narrower than the raw age of the universe suggests. The universe spent most of its existence building the raw materials, then building the first stars, then running through enough stellar generations to produce heavy elements, then waiting for those elements to coalesce into rocky worlds, then waiting for life to emerge on those worlds, then waiting for intelligence to emerge from life. By the time anything that could build a radio telescope existed anywhere, the universe had already used up the first 2/3 of its current age. We are late arrivals in a universe that spent most of its history not being ready for us. And even now, the conditions that made us possible are not evenly distributed through the cosmos. The universe has been slowly becoming more hospitable, but not everywhere, not at the same rate, and not in a way that tends to synchronize the appearance of civilizations with each other. This connects to something worth examining as its own topic: the cosmic timeline of habitability. Early models of the Drake equation, the mathematical framework developed by radio astronomer Frank Drake in 1961 to estimate the number of communicating civilizations in the Milky Way, tended toward optimism when generous assumptions were used. Plug in favorable estimates for each factor and you get numbers in the millions. But the Drake equation doesn't capture the temporal dimension of the problem with enough granularity. It treats the galaxy as if civilizations arise at a roughly steady rate and as if different civilizations are broadly contemporaneous. The reality is considerably messier. The galaxy evolved. The rate of star formation was much higher in the past than it is now. Most stars in the Milky Way formed between roughly 8 and 10 billion years ago. Those early stars seeded the interstellar medium with heavy elements. Subsequent generations of stars formed with increasingly favorable chemistries for planetary complexity and, potentially, biological complexity. But those timelines cascade and stretch. A star has to form. Its rocky planets have to coalesce and cool, a process that typically takes tens to hundreds of millions of years. Liquid water has to persist on the surface long enough for chemistry to complexify and life to emerge. On Earth, this took roughly 500 million years after the surface solidified enough to hold liquid water. Life has to then complexify over hundreds of millions of years through the development of multicellularity, animal body plans, and nervous systems capable of supporting intelligence. Intelligence of a general enough kind has to then develop the specific cognitive tools, language, cumulative culture, tool use, abstract reasoning that allow technology to emerge. Technology has to then progress to the point of radio astronomy. On Earth, from the first single-celled organisms to Fermi's lunchtime question, that chain took roughly 3.8 billion years. Then that civilization has to be in its transmitting phase at the same time as another civilization that also managed to navigate all of those steps and also happened to be within communicating range. Not just existing, transmitting, in a detectable way. Simultaneously, nearby enough for the signal to arrive above the noise floor. The number of civilizations that satisfy all of those conditions simultaneously within the same region of the galaxy at the same cosmological moment may be extraordinarily small. Not because life is rare in an absolute sense, but because the timing requirements are extremely constraining. You could have a galaxy that produced billions of civilizations over its history, each one thriving for thousands or millions of years, and still have long stretches of cosmic time during which no two are simultaneously active, close enough, and detectable to each other. The statistics aren't just against us. The statistics are actively manufactured by the way the universe assembles itself over time. Zoom out, now, beyond the Milky Way. The observable universe contains roughly 2 trillion galaxies. If the Milky Way alone might host millions of civilizations at various points in its history, then across 2 trillion galaxies, the numbers seem to explode into incomprehensibility. There should be something out there producing detectable signals. But here's the problem. Almost none of those galaxies are within any meaningful communication range. The nearest major galaxy, Andromeda, is 2.5 million light-years away. Any signal from Andromeda that we could detect today left that galaxy 2.5 million years ago. Whatever civilization might have sent it existed 2.5 million years ago and is either a completely different entity today or simply gone. The Virgo cluster of galaxies, which contains over 1,300 galaxies and forms the heart of the larger Virgo supercluster to which the Milky Way belongs, sits about 54 million light-years from Earth. Any signal from civilizations in those galaxies that we could detect today was sent 54 million years ago. 54 million years ago on Earth, the dinosaurs were already gone, and the earliest primates were just beginning to appear among the small mammals diversifying across the planet. The world those signals would describe is a world without humans, without our ancestors as we'd recognize them, without anything that ever looked up and wondered. Signals we could detect from Virgo cluster civilizations would describe a cosmos almost unimaginably distant from our own moment. We're not separated from other galaxies, only in space. We're separated from them in time. The further away they are, the older the signal. The universe's finite speed of light means that the scale at which other galactic civilizations could plausibly communicate with us in any meaningful, responsive sense is essentially zero. Even within the local group, the gravitationally bound collection of galaxies that includes the Milky Way and Andromeda and about 80 smaller companion galaxies, the nearest substantial neighbors are hundreds of thousands of light-years away. Intergalactic contact is not a hard problem waiting to be solved by better technology. It's a structural impossibility enforced by the combination of distance and light speed and the age of the universe. There's another barrier that doesn't get enough attention when people discuss the silence: the expansion of the universe. Distant galaxies are moving away from us, not because they're traveling through space at high speed, because space itself is expanding. The fabric of the cosmos is stretching, and everything embedded in it is carried apart. This was first firmly established by Edwin Hubble in the 1920s, when he noticed that the spectra of distant galaxies were shifted toward the red end of the electromagnetic spectrum. A Doppler-like effect caused by the expansion stretching the wavelength of light as it travels. The further away a galaxy is, the faster it appears to be receding. This relationship is described by what's called the Hubble constant. Beyond a certain distance, known as the Hubble radius, galaxies are receding